Hello students, Stride here again. Today we're going to look at section 17.3 titled Behavior of Waves. This is just an illustration of some ripples on a pool, visible on the bottom, light shining through the surface waves. So here we're going to look at how waves interact together, how they interact with other things. Reflection, one of our types of wave behavior. Reflection, when a wave bounces off the surface it cannot pass us through. So remember, reflection just means bouncing back. Reflection will not change the speed or frequency of a wave, but it might cause it to flip upside down. You can observe this if you're looking in a spoon. If you look in a spoon as a mirror, you may see your reflection upside down. Refraction, another interference, is the bending of waves as it enters a new medium at an angle. So reflection, bouncing back, refraction, bending. And why this happens, given here, when a wave enters a medium at an angle, refraction occurs because one side of the wave moves more slowly than the other side. It's a good illustration here with the lawnmower. As this lawnmower gets off into the gravel, off of the grass, when it's on the grass, it's moving faster. When it's on gravel, it moves slower. This causes the lawnmower, instead of to go straight, causes it to curve as the two wheels are moving different speed. It's essentially the same idea of what's happening during refraction. You get this effect, illustrated lawnmower on a car. If your car tire drops off the edge of the highway into some gravel or grass or dirt, it's going to change its speed and it can cause your car to veer off. Ocean wave approaches the shore at an angle, the wave bends or refracts. Is one side slowing down more than the other? Go through these slides. See illustrated where the waves are bending, right there. And here, as the water gets shallow, it's like a new medium. So it's entering a new medium. As one side enters the shallow water before the other, it slows down, causing the wave to bend. If it's parallel to the shoreline, if it's coming in parallel, not going to be any refraction. Always has to be entering at an angle. Now here we get diffraction. And it's also bending, so both refraction and diffraction are bending. Refraction, bending as it moves into a new medium. Here, as it goes around an obstacle or passes through a narrow opening. Now, it's going to diffract a lot more if the wavelength is large compared to the size of the opening or the obstacle. So waterways are going to spread out as they pass through a narrow opening. You'll see a pattern much like if you toss a pebble into a pond, it's real circular ripples. Also happens when it bends around an object. If you're standing around the corner from somebody, you can still hear them talk to you because the sound waves will diffract around the corner. Again, The larger the wavelength, and compared to the size of the opening or obstacle, the more diffraction you're going to get. A couple pictures of the diffraction. As the waterways encounter this opening, you start to see the curvature. Or as we encounter an obstacle in part B here, you see the curves form in this area here. Interference, another type of wave interaction. Two or more waves overlapped and combined together. We get two types called constructive and destructive interference. Constructive interference, when we get a larger displacement, they combine. Destructive, when they kind of cancel each other out, and we get a smaller displacement. In sound, if it was constructive interference, you get louder sound. If it's destructive interference, you're going to get a softer sound. So, illustrations of constructive interference. Combine wave 1, wave 2 together, we get wave 3, which has higher amplitude. So with constructive interference, we tend to get increased amplitudes. Destructive interference, illustrated here, combine wave 1 and 2 together to get wave 3. And they cancel each other out a little bit. We get a reduced amplitude. If they completely cancel it out, that's going to be a phrase we'll call complete destructive interference.
The office, Phoenix Martin to the office.
And you can get what we call a standing wave. A wave appears to stay in one place, does not move through the medium. Standing wave forms if it's only a half a wavelength or a multiple of half a wavelength that's in the exact length of a vibrating chord. Standing waves are generated as we have both interference going on and some reflection going on. And at the right frequency, interference between that wave and its reflection can generate a standing wave. Yeah, here we have things called nodes and antinodes. Node has no displacement. Antinode is where it results in a crest or a trough and will always occur halfway or midway between two nodes. At the nodes, we get that complete destructive interference. Here's an illustration of the standing waves. Here, all you're going to see in these is just the waves are going. You see the up and down motion, but you won't see the left and right motion. Standing waves. You can see standing waves generated on many musical instruments and string instruments like a guitar. We set up standing waves. Also sets up standing waves in wind instruments. And then you got a few questions here. Make sure you know the answer to these questions. So that's all for 17.3. That's all for now. Until next time, this is Strike.